Today I will be putting out a short video where I will go through the first roughly like a third of last year's exam. Uh, the remaining bits will be done in separate videos. I felt it would be too long to have them all in one, partially due to my own time constraints. So I think we can just start with it. The exam itself was on Inspera, as it's going to be this year as well. Uh, and it's going to be a mix of various formats of questions. Some of them, like this, will be a plain text answer. Some will be more multiple choice or filling out numbers. Typically, for instance, filling out an adjacency matrix would be the type of exercise you could get. So let's just start with the first exercise. Start with the basics. So here we have a network. The nodes are labeled with node identifiers, and the edges are labeled with numbers, which are reasonable to interpret as edge weights. So the first question is, what is the degree of the node? As we've discussed in class, the degree of a node is essentially its number of neighbors in the network. Or how many edges connect through that node. Those terms are equivalent. So in this case, for instance, node 1 has only one link going into it and only connects to node 2. So node 1 has a degree of 1. Node 2 has 4 links, so it has a degree of 4, and so on. The edge, or the numbers on these edges here, are entirely meant to distract you. When we talk about degree, we only mean the number of edges. We don't care about their weight. If we were to ask what is the strength of a node, then suddenly the edge weights become relevant. But for the notion of degree, the degree of a node is the same whether the network is weighted or unweighted. Strength is the term that refers to the sum of the weights. So for instance, node 2 would have a degree of 4, but a strength of 12. While node 5 also has a degree of 4, but it would have a strength of 16. 5 plus 5 equals 10, plus 3 plus 3 equals 16. So yeah, that's what we mean by the degree of the node, simply the number of connections. And so the second follow-up question here is, compute the average degree of the above network. And now there are two ways to do this. There is the simpler, maybe more, or arguably simpler way in the sense that it's more literal. It's computing the average degree, but it's less efficient. What you can do is you just count the degree of every node. You say that node 1 has a degree of 1, node 2 has a degree of 4, and so on. And you will get 10 numbers, and then you can average those. That is pretty straightforward. But another thing that we also know is that each edge contributes 1 to the degree of each node. Or 1 to the degree of each node on each end of it. So it contributes 1 to the degree of 2 separate nodes, which means that the sum of the degree in a given network is going to be 2 times the number of edges. And that means that the average degree is simply the number of total edges divided by the number of nodes. The total number of the sum of the degrees divided by the number of nodes. And since the sum of the degrees is 2 times the number of edges, since each edge contributes 1 to 2 different to the degree of 2 different nodes, we can just count all these edges, double that, and divide by the number of nodes. So we see here these nodes are nice and numbered: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 nodes, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 edges. And so the average degree is 2 times the number of nodes divided, 2 times the number of edges divided by the number of nodes, which equals 2 times 13 divided by 10 equals 26 divided by 10 equals 2.6, which is the average degree of this little network. Okay, let us go on to the next question. The next question here is on the topic of clustering. Here we have the same network as before, or yeah, it's the same, just without the node labels or the edge labels, and we're asked to explain with words what the meaning of the clustering of a node is. And so clustering is essentially the interconnectedness of a node's neighborhood. What is the likelihood for your connections to independently be connected to each other? In a more formal sense, we can say that the clustering for a given node is the total number of triangles that are formed by that node and its neighbors. So for instance, we see for node 2 it forms a triangle with n3 and n4 while not with n1 and n1, n2, and n3 do not form a neighbor, nor do n2, n4, n5, or anything like that, for instance, right? We have here the only triangle that n2 is involved with is our 3-click, if we want to be proper or technical with our terminology. The only 3-click that n2 is a part of is this n2, n3, n4. And so we know that it has one of those. And how many theoretically could it have? Clustering is a number that goes from 1 or from 0 to 1, where 0 is something you'll have for a node where none of its neighbors are connected to each other, while a clustering of 1 is something you'll see in a node where all of its neighbors are connected to each other. And so it makes sense that if you want to have an expression to compute this, you divide the number of triangles by the total maximum number of triangles you could have. And the question then is, how many different ways can you, for node 2, how many theoretical combinations could you have of its 4 neighbors to have connection? And well, that means how many ways can we take 2 out of 4? And that is 4 multiplied by 3 divided by 2. It's essentially, you can think of it as a square where nothing can connect to itself. So you remove the diagonals. And then you only take the upper triangle of that diagonal because it would be symmetric. So here we see that we have 4 neighbors, which means 4 times 3 is 12, divided by 2 is 6. And 1 triangle. So we can actually go straight into question B from here. So the clustering of node 2 here is, so let's call it just C2 equals 1, since that's the number of triangles, divided by 4, which is the degree, multiplied by 3 divided by 2, which is 1 divided by 6, which is 0.166, repeating. Let's look at node 3. Now node 3 is part of 1 3-click, so C3 is still, the numerator in our expression is still going to be 1. But node 3 has a degree of just 1, of just 2. So then we get, actually we can just say Cn equals number of triangles divided by Kn multiplied by Kn minus 1 divided by 2. So C3, that's 1 plus 2 by 1 divided by 2, which is 1. And that's clear. There's no way you could add more connections between the neighbors of N3 that would increase the interconnectedness of its neighborhood. It has 2 neighbors and they're connected. That's as far as you're going to get. And now let's finish off with N8. Well, N8 has, like N2, 1 triangle in its neighborhood. It's this n8, n10, n9. And in addition to that, it has only node 5 as neighbors. So it has a degree of 3 and one triangle. And that means that C8 equals 1 divided by 3 multiplied by 2 divided by 2, which equals 1/3. And so that would be the clustering for these 3 nodes. Okay, on to the next question. So what is the diameter of the above network if we either ignore the edge weights and if we include the edge weights? Now, the diameter of a network is the longest of the shortest paths between any two nodes in the network. That is, we want to find the 2 nodes in the network that are the furthest apart from each other. If you it's not in terms of what is the longest path, because sometimes you can have very long paths. If you allow yourself to loop over where you've been, you can have infinitely long paths, but that's not the shortest path. We want to find the 2 nodes that are the furthest away from each other in terms of shortest paths, and then find out exactly what that distance is. And so if this was a very big network, we would have a bit of an exercise in front of us, and there's algorithms that have been done to do this efficiently by computers, because it's not an easy task for a human to do quickly for a large complicated network. But this is a pretty simple network. So we can sort of intuitively see by hand that, well, it would be something on one side on the left here to something on the right here. And that would be here. We see that from this like mixed point, or like connection point between n2 and n5, the furthest away from n5 is either n10 or n9. Similarly, on the other side from n2, everything is really just a distance of 1. So the most distant pairs of nodes we have is really any combination of n1, n3, and n4 combined with, or any of these 3 combined with any of either any of either n10 or n9, since these are 2 more steps away from n5. Which means that our diameter would be, for instance, if we take this path here, it would be 1, 2, 3, 4. So that is AD equals 4. With edge weights, it becomes a little bit more complicated, because now we can not just necessarily look at it. In fact, we see, for instance, that if we just look from n5 to n8 or to n10, the shortest path is affected by this. Or the distance from n5 to n10 is 3 plus 2. And the distance from n5 to n9 is 3 plus 2 plus 1, a total of 6. Which is actually, even though you have to go through 3 links, it's a much shorter distance than what we have. Or no, yeah, it's not a much shorter distance, but it's a relatively short distance compared to what we have from n5 to n6. That, even though it's just 1 step, we have a distance of 5. But okay, what can we find here? So if you look here, this edge 5 here is a good candidate to start, because any of these will have to connect through something here through n2. And that means that n2 is definitely not going to be involved in any of the longest paths, because any of the shortest path between this and anything on this side will have to go through, and will so necessarily the path from n2 itself to anything here will be shorter than anything we have on this side. And so we see that the one that's the furthest from n2 on the left is n4 with a distance of 5. If we look on the right side, we can sort of take the same approach. And so the question is, on the right side, what is the furthest away from n5? And how far is it? Well, we see that in this case is specifically n10. n6 is a distance of 5 directly, n7 and 8 are both a distance of 3. And 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 10 becomes a distance of 3 plus 2, which is 5. And so the longest shortest path in this network is n4, n5, n2, n5, n7, n10, n9. So then becomes BD equals 5 plus 5 plus 3 plus 2 plus 1, which equals 16. And that is the weighted diameter of our network. Okay. Let us now move on to shortest paths, or stay on the topic of shortest paths if you want to look at it that way. So the question, we are provided here n6 and n9. That is this node here and this node here. What are the shortest paths between n6 and n9 if the network is considered to be unweighted? Well, here we can see that it's pretty straightforwardly either this n6, n7, n10, n9, which is 3 steps, or equivalently n6, n5, n8, n9, which is also 3 steps. If we include the edge weights, the paths here become 4 plus 2 plus 1 is 7, and here the other path is 5 plus 3 plus 6, which is 14. So in this case, we will have, for A, we can just write the answer. It would be n6, n7, n10, n9, or n6, n5, n8, n9. For B, it is only n6, n7, n10, n9, since there is no other way. Like, it's pretty intuitive that if we find this this one here, that's 7, and anything, it can't be anything through n8 because both of those edges are 6, and so all the other weights are above 0, so it can't go through there. And once we're here, what is the closest from n7 to n6? Well, we only have 2 choices. We have 4 here, or 3 plus 5, and 4 is obviously the shortest one. Okay. So the next one is a different format of question. Here we have boxes to tick. As you can see, we can have any or all or none of them in any combination that are true of these statements. And so what you're asked is, well, which of these statements are actually true? So let us go through them one by one and discuss them a little bit. So the first statement is, are scale-free networks particularly immune to epidemics? And what we find with scale-free networks is that they are, in terms of maintaining connectivity, they are highly robust to the removal of random nodes, while very weak to the targeted removal of nodes. And in terms of epidemics, this means that even though a very small amount of nodes are infected, the hubs serve as interconnectors. Even if you were to disconnect a lot of nodes, you would still, if you do this randomly, you will have if you remove a lot of nodes, an epidemic would still be able to spread on a scale-free network, and generally, scale-free networks are very vulnerable to spreading processes because of the prevalence of the hubs. And so this statement is not true. Scale-free networks are not particularly immune to epidemics. So the second question. The configuration model can be used to generate scale-free networks. So first is, what do we mean by a scale-free network? Primarily, we mean a network that shows a power law distribution. where essentially that the degree distribution follows an exponential function. That forms a straight line if you do it on if you plot it out on a log-log plot. And so it has a very heavy tail relative to a lot of other distributions, such as, for instance, a normal distribution. Now, the configuration model is defined by the fact that you can give it any degree distribution and use that to generate a model, or any degree distribution which satisfies some conditions, such as that the sum of the degrees has to be even. But it is absolutely valid to give a power law degree distribution to the configuration model. If any degree distribution is feasible for any network, the configuration model can be used to generate it. And so, and since a scale-free network is defined by its degree distribution, and which obviously is feasible since scale-free networks exist, that means that we can generate them with the configuration model by generating a power law distribution. That is actually an alternative to generating to preferential attachment-based models in terms of creating scale-free models. Is you just generate a power law with a random generator. There are various ways to do that that sort of fall outside the scope of this class. And then you just give that as a degree sequence to a configuration model, and you will get a scale-free network from that. So that is true. Second statement. Duplication differentiation is a form of preferential attachment. So duplication differentiation is a model where we start with a given network, and at each time step we might duplicate some nodes, and then we might do a bit of rewiring, either around the node that was just duplicated, or the node that was just produced, or anywhere else really. We have a little bit of freedom in how we define our rules here. And a characteristic part of this is that when you duplicate a given node, you will create a new node that is connected to all of its neighbors. And that means that on any duplication, every node that is connected to the one node that was chosen out at this time step will gain an increase in degree. And the thing is that if you're a highly connected node, if the duplication process picks a node at random from the network, like even in a balanced manner, the more neighbors you have, the more likely you are to have one of your neighbors duplicated. Because if you have, say, 100 nodes in a network, and you have 10 neighbors, then, well, you have a 10% chance of the node being duplicated being one of your neighbors. If you only have one neighbor, then you have a 1% chance of the node being duplicated being one of your neighbors. So that means that over time, the number of connections you gain will be proportional to the number of connections you had in the first place. And that is, in fact, a form of preferential attachment. So that statement is true. Bipartite networks typically exhibit high clustering. Well, a bipartite network has two sort of interpretations, or there's multiple ways of interpreting them. The intuitive one, the simple one, and the one that's really sufficient to answer this question is that a bipartite network is one that consists of where you can group the network into two different sets of nodes. And you can assign each node to one of two groups. And a node that connects to that is part of a given group can only connect to nodes in the other group. You cannot connect a node to another node of the same group. And what that means is that if you are a node with a certain amount of neighbors, then all of your neighbors must be in the other group than what you are. But that also means that they are in the same group, which means that your neighbors cannot connect to each other directly. And so, in fact, not only do bipartite networks not exhibit high clustering, but almost by definition, if not by straight definition, but by a strict implication of the definition of bipartite networks, they can't exhibit clustering at all, because you cannot have any three-clique or any clique of any sort in a bipartite network, because that would conflict with this classification into two groups that that it underpins the concept of bipartite networks. The stricter definition, the formal definition of bipartite networks, is that you have no cycles, no paths that return to their original node with an odd length. That is the strict definition, and the mathematics behind that is a little is not something to worry about. And a triangle is a cycle of distance 3, which violates that strict definitional requirement for a bipartite network. So again, this is thoroughly not true. And our last statement here is that the Watts-Strogatz model exhibits small world properties for all parameter choices. Now, the Watts-Strogatz model is a comparatively simple random model that was made to reconcile the concept of clustering with the Erdős-Renyi model. Because the Erdős-Renyi model was good at explaining the small world phenomenon, but it had very low clustering, which is uncharacteristic of many real networks. So Watts and Strogatz wanted to develop a random network model that would both exhibit small world properties and high clustering. And so the way this is done, and I'm actually going to go into our textbook here, is that you start with a given cycle here, where every node connects to, or a ring rather, where every node connects to neighbors on that ring a certain distance out from it. And then with a variable parameter p that can go from 0 to 1, you will rewire some of those. And we see that as you do that, average distances tend to fall, while clustering stays high for a while until it drops off as well. But so typically Watts-Strogatz models do show small world properties, but the framing of the question is does it show small world properties for all parameter choices? And by any technicality, p equals 0 is a valid parameter for a Watts-Strogatz network. This would be still a Watts-Strogatz network with p equals 0. Just in the same way as you can say that a clique is an Erdős-Renyi network with a very high degree, or like with the total number of edges picked to be the theoretical maximum. And so, in the strict sense of the question, the Watts-Strogatz model does not exhibit small world properties for all parameter choices. Okay, on to the next question. So, same format, like checkboxes, any of them can be true or not. And this here, this problem here relates to the 7 bridges of Königsberg problem that we started this class off with. And the question is, for which of these can we have such a walk where you can cross every edge once, but only once? And of course, you are welcome to try your best and exhaustively search through it. And if you're anything like me, maybe as a kid you tried this, drawing a closed square without lifting your pen off the table, and just figured that it wasn't possible. But the formal definition of, or the formal requirement for such a Königsberg walk to be possible is that either all the nodes have an even degree, or only 2 nodes have an odd degree. Since every time you enter a node, you must also leave it, unless it is your first or your last node, which means that for every incoming edge, you also must have an outgoing edge on your walk, which means that the total number of in and outgoing edges must be a multiple of 2. So the degree is the degree is a function of 2. Again, the walk has a direction, but the network is still undirected. So okay, let's look at the first. Well, this is a for-clique, which means that you have 4 nodes, everyone is connected to the others, and that means that you have a degree of 3 for each, and that is more than 2 nodes with an odd degree. So A is not a valid network for a Königsberg walk. If we look at B on the other hand, this is a 5-clique, right? We have 5 nodes all connected to the other 4, which means that every node has a degree of 4. And so it is valid. We can actually try to find one. We can do a pretty simple one. It will just be, first you walk around this outer pentagon, bam, 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 bam here. And now you've done all the other ones, and you're stuck with, or you're left with a pentagram in the middle, where you can do the path here, where essentially you skip 2 jumps at a time relative to your previous lap. So then you go here, 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 and here, and now you would have looped through the entire network. So for B, it is valid. For some reason, Inspera shuffles the order on questions, so it falls out of order here. Okay, let's look at C. Same criteria here. Now here it's a lot harder to just trace one out by hand automatically, at least if you're not sure if one exists. So, but again, the trick is just count the number, or just count the degree for each node. So if we see this first one here is 4, so that one is fine. This one here is also 4, so also fine. This one here is 4. 1, 2, 3, 4, also fine. This one here is a bit trickier to count because it has a lot of edges and they go in all directions, but 1, 2, 3, 4, 5, 6, so that's fine. And this the last one here has a degree of 2. So these are all even numbers. And so it is valid for a Königsberg walk. If we want to identify one here as well, we can start as before, walk around like this outer loop each time, and then what we could do is we could cross over the diagonal. We don't really have a choice. Then we can't really go back because then we'd have expended everything on the top left corner here, but we can go through the second one here. We only use this outer one on the first go. Cross over this other diagonal, down here, and back. That would be a valid Königsberg path for network C. For network D, what do we have? We have this one here has a degree of 4, that's fine. This one has a degree of 3, not fine unless we have exactly one other with an odd degree. And this one has a degree of 3, that's okay. So then we're at 2 nodes with odd degrees. But this one here also has 3. So that means we have at least 3 nodes with an odd degree. So D is not a valid network for a Königsberg walk. And over to the last question that we're going to be doing in this session. Here is a matrix, and the question filled with ones and zeros, like adjacency matrices for unweighted networks typically are. And the question is, why is this not a valid adjacency matrix for a network? So, and this wouldn't, it's not that it's invalid for directed networks or for undirected networks. For neither directed or undirected matrices would it be a valid adjacency matrix. And what we see here is that one of the first parameters you can often check in a matrix is its dimensions. It's a 5 columns and 7 rows matrix. And an adjacency matrix is necessarily square, because it says each row, all the rows correspond, or all the rows correspond to a column. Row 1 should correspond to to a node. Sorry, all rows correspond to a column. So row 1, I keep myself. All rows correspond to a node. So row 1 corresponds to node 1. Row 2 corresponds to node 2, and so on. But the same is true for the columns. Every column should correspond to a node. So column 1 corresponds to node 1, column 2 corresponds to node 2, and so on. And since each node is represented once and exactly once in both the rows and the columns, you must have the same number of columns and the same number of rows. And so that means that every adjacency matrix is square by requirement. And since this matrix isn't, it is not a valid adjacency matrix. So yeah, this is a small sample of the type of questions you can expect on an exam. A little bit of of the classical stuff that you've seen. Exercises, some things that I hope force you a little bit to think and put the things you learned into context. I feel like, for instance, this is a subject that hasn't been mentioned explicitly in like the notion that adjacency matrices are necessarily square, but with a good understanding of the class material, you should be able to instinctively say that no, this isn't working, and yeah, no, adjacency matrices must be square. That it doesn't make sense that it wouldn't be. So yeah, I'll leave you off at this, and after in 1 or 2 days, I'll follow up with the next